Those are online, are you? Those are online, are you able to hear me?
Yes, sir.
Those are online, are you able to hear me?
Yes, sir.
Yes, sir. Sir.
Yeah, is the voice clear?
Yes, sir.
Yes, sir.
Okay.
Myself, Narayani CM, I had a great experience.
Proceed. Can I just have a confirmation from those who are online as well? Shall we proceed?
Okay, sir.
Okay, sir. Sir, okay.
Okay, results. So basically, we saw two important derivation. Simple only. So we saw two important terms. One was drift velocity, and then we saw mobility. For drift velocity, we saw the derivation, right? So remember how we are supposed to do. First is when you get a conductor, the conductor will have three electrons inside which are going to be random motion because of thermal agitation. Then when you connect it across a potential source, what happens to it? They start moving in an aligned path, right? So the electrons start moving from negative to positive terminal, whereas the current is considered to be from the positive to the negative, right? So this happens, and because of which there is going to be an electric field generated, and due to the electric field, there will be force, and due to the force, there will be acceleration, and due to acceleration, you get final velocity. And the average of all those final velocities is what we call it as drift velocity. So the average of that value, that is the drift velocity divided by the electric field, is given a term called as mobility, which is going to help us understand how mobile the charge is in the conductor. So drift velocity is a vector quantity, whereas mobility is a scalar. Right? Now, we are going to proceed to the next important topic. So I'm not going to give you the heading now. First, we'll see the derivation, then we'll give the read to the derivation. If at all I have a conductor like this, where you have the free electrons present in there. The free electrons are going to randomly move inside the conductor. But as soon as you connect it to the potential source, there is going to be an electric field that is getting generated. Now let me say the length of the conductor is going to be L. And I will take the area of cross section of this conductor to be A. And I'm saying that the number of electrons inside the conductor. So number of electrons inside the conductor, I'll call it as capital N. Wherever you have area of cross section and length, is there a possibility for you to define a parameter called volume? So what is going to be the volume of this conductor? So volume is going to be area multiplied with the length. Right. And one point that is to be kept in our mind is there is drift velocity existing in the opposite direction of the electron because Vt is equal to minus E into capital E divided by N. So with drift velocity and electric field are always in the opposite direction. Correct. Now having said this, if at all I am interested to calculate once the drift velocity is attained, I can confidently say that there is current constituted with it. Till then there was no current. Why? Because of the random motion. Whereas now the drift velocity is current only in one direction. So there is definitely current existing with it. Right? So if I need to understand how much is the current flowing through the conductor, then I will say I is equal to the amount of charge that is moving with the right? The amount of charge divided by the time. Can you see this? Right. So it is going to be the amount of charge now the question is, if I take this as equation number one, the first question that I need to answer is, how much is the charge that is constituted by the conductor? Logic is very simple. From the concept of quantization of charge. If there are n number of electrons present inside, and the charge of each electron is going to be E, then you say that Q is equal to capital N into E. So which I'll call it as second equation. Now the next question I'm supposed to answer is, how much is the time taken for me to say that the current I is constituted by this? So how much is going to be the time? So if you see the time is equal to distance divided by speed. Now listen to this carefully. You can always say that the current is flowing through the circuit. When I say current is flowing through the circuit, it should be a continuous process. So when is it said to be a continuous process? When an electron starts from the negative terminal and moves to the positive terminal. So if I take one electron, how much is the time it is going to take to travel from the negative charge to the negative terminal to the positive terminal? It is going to be the distance by speed. How much is the distance it is traveling? It is traveling with L. And the average of speed of each electron. The average velocity is Vd. So L divided by Vd. Let me call this as 3. So I will take the third one and substitute it into second one. Can you do that? So I will take the third and substitute into second. So I will take the third and second and substitute it into one. Right. So I will be equal to what is the value of Q? It is going to be N into E the whole divided by L divided by V. So it is going to be N E divided by L into V. What I do is, since length alone is getting involved, right? So instead of calculating the number of electrons inside, it is easy for us to calculate another parameter called as number density. For me to get the number density, what I need to do is, I need to divide the number of charges with unit volume. So for me to get volume in this expression, what I do is, I will multiply it with A and divide it with A. And when I multiply with A and divide with A, I get N E A V D, the whole divided by A into L. Got it? So this capital N divided by A into L, we can give a name. Number per unit volume is what is called as number density. I would like to stress on one point. In physics, wherever you are dealing with number, so it's this N is not restricted only to this chapter. In other cases also you see something like number of terms per volume. Like when we talk about magnetic effects, like how we learn in your 10th grade, right? So wherever you see number, always use capital N. Wherever you see number density, always use small n. So n divided by this is going to be small n into E into A into BD, and this is the expression for the current that is going to the conductor. So to put it simple, I is equal to small n into E into A into BD, where small n is called as the number density, and this is going to be the required relation. Hence, the name of the topic is relation between electric current. Relation between electric current and velocity. This is the name of it. So I hope it is clear, right? Those who are online, is it clear?
Clear, sir.
Yes, sir. Let's make a note.
Clear, sir.
Clear, sir. Shall I proceed? I wrote that. So now we know that I is equal to NEA into VD. Right. So if I rearrange this equation by bringing A to the left hand side. So if I make it I divided by A, then I get NE into VD. Right. Then this I divided by A is given a name called as J. Can you guess what the name would be? The amount of current flowing per unit area. Right? So if you observe, it is the amount of current flowing per unit area, and this is given the name called as current density. So it's called as current. Am I clear with this? So this J will be equal to N into E into VD, right? It's going to be equal to N into E into VD. And remember, it is going to be a vector quantity. So in this case, the vector which is decided because it is plus. It's a vector quantity. And what is going to be the SI unit here? SI unit is going to be ampere per meter square. So this is going to be current density. So please make a note of this. Let us see. Who's online? Shall I proceed?
Okay, sir.
Okay, sir.
In progress.
This room. Yes. Yeah, those who are online are able to see my screen.
Yes, sir.
Yes, sir.
Those who are online are able to see the screen.
Yes, sir.
Those sorry, yeah. No speak. Those who are online are able to see.
Yes, sir.
Sir. Okay. Solution. Now, I'm not going to reveal the topic again. Okay. We'll see. If I have a conductor like this, which contains n number of electrons. If I take this to be the positive charge, this to be the negative charge. And we know that the electric field is directed in this direction, and this is going to be the length of the conductor. We know that I is equal to NEA into AD, and let me call this as equation number 1. Okay. Where N is the number density, is the charge of electron, A is the area of cross section, B is the drift velocity. Now, we know that Vd is equal to small e into capital E divided by M into tau. You can see this. Right. Let this be equation number 2. Take the second equation and plug it into the first one. So combining these two, we are going to get I is equal to NE A into, in the place of BD, can I write it as E into capital E divided by M into tau. Right. So E into E will get multiplied, it will become NE square. So it will be NE square A into E divided by M into tau. Right. So let me call this as the third expression. Now tell me, what is going to be the relation between the potential difference and the electric field? So we know that E is equal to V divided by L. Because it is a potential gradient. Electric field is the negative of the potential gradient. But since I already know the direction, I am not taking the minus sign into consideration. So it will be the potential difference divided by the distance of separation between them. So the V is not potential, it is the potential difference divided by the length, the distance of separation between them. Right? So I will take this as 4. Now, taking this 4 and plugging into 3, what are we going to get? If you observe, I will be equal to NE square A divided by M into, in the place of E, I can write it as V divided by L into tau. Makes sense? Right? Now, if you observe, I will leave this V this side. I'll take all other parameters to the reference. So can I say that V is equal to, right? Can I say that V is equal to M into L divided by N E square A into tau. So m into L divided by n e square a into tau. The whole thing multiplied with I. So if you observe, this parameter is called as R, which you already know. So if you rewrite this equation in the simplified form, this is going to be taking the form V is equal to I into R, and this is the derivation for Ohm's law. Right? Where R is going to be equal to m into L divided by n e square a into tau. Negative ones. Clear to see? Those who are online, shall I proceed?
Sir.
Listen. Now, we understood that R is equal to m into L divided by n e square a into tau. Okay. And the expression that we wrote is V is equal to I into R. Now, if you recollect the statement for Ohm's law, it says when the temperature of the system is constant, right, the current going through the conductor is directly proportional to the potential difference. Right. So the current going through the conductor is directly going to be proportional to the potential difference, provided the temperature is constant. Now, this expression will help us understand why the temperature is supposed to be constant. If you observe, can I write this R is equal to m divided by n e square a into tau, the whole multiplied with L by A. So when temperature changes, remember length will change because it's a conductor, it's a metal. Area of cross section will change, and most importantly, the relaxation time will change. Why? Because ours So here I put A already here. So I will write R is equal to M divided by N E square tau into L divided by A. If you observe, if the temperature is changed, the length is going to change, area of cross section will change, and most importantly, the relaxation time will change. How is it going to change? As the temperature increases, so as the temperature increases, kinetic energy increases, whereas the relaxation time decreases. Okay, because when the speed is going to increase, the amount of time that the existing between successive collisions is going to decrease. Okay. So that is the reason why when R is introduced as a constant of proportionality, what is importantly, what is supposed to be constant? The first, the T temperature. That is why the statement always starts saying that and the temperature of the conductor is kept constant, then the potential difference and the current are proportional to each other. Able to understand? Okay. So this is next is if you observe, I wrote R is equal to M divided by N E square tau into L divided by N. This M divided by N E square tau, M divided by N E square tau can be called as resistivity. It can be called as resistivity. That is why in your lower grade you would have learned this expression R is equal to rho into L divided by. Okay. So you get R is equal to rho into L divided by. Now if you observe, since rho is equal to M divided by N E square tau, resistivity also depends on temperature. Oh. Because resistivity is going to change with respect to the relaxation. So tell me what is going to happen. We know that when the temperature is going to increase, kinetic energy will decrease and relaxation time will decrease, as a result of which resistivity will increase. Same is the case with resistance. Sorry, kinetic energy increases. Correction here. Kinetic energy is going to increase. The relaxation time is going to decrease and the resistivity increases. Same is the case with respect to resistance. Am I clear with this? So please make the note of this. Can we proceed? So since we saw the concepts related to the resistance and resistivity being dependent on temperature. Like since we saw that they both are dependent on temperature. The next concept we'll see. So the next concept that we will see is so the next concept will be temperature dependence. Temperature dependence of resistance and resistivity. So temperature dependence of resistance and resistivity. If you observe, if I take the conductor to be in this way, if I take the electric field, it's not needed actually, electric field is not needed. If I take the initial resistance of this conductor to be Ri, and if I take the final resistance to be Rf, so when will this final resistance occur? When either temperature is supplied to it or taken away. That is when you supply heat to it or take away, right? Its temperature is going to change. So when there is a temperature change, R final will be equal to R initial multiplied with 1 plus alpha into delta T. So R final will be equal to R initial into 1 plus. Just so R final is equal to R initial into 1 plus alpha into delta T, where this R final is going to be the final resistance. Right. Ri will be the initial resistance. Alpha is going to be the temperature coefficient of resistance, and delta T is going to be the change in temperature. So this is going to be the expression for the relation between final resistance and initial resistance according to the change in temperature. Now, if I extend the same concept to resistivity, it will be like this. Rho final will be equal to rho initial into 1 plus alpha into delta. Okay. So this is the one first. Am I clear? See, there are some important problems based on as we discussed before. First, I'll complete the theory, then I'll do some problems. Okay. So, the next concept that we are supposed to see is resistors in series. Okay. So, if you observe, if I take these three resistors and connect them in series across a potential difference of V, okay, where this is going to be R1, R2, and R3. Okay. So first thing that you need to have in your mind whenever you see series connections, current across all resistors will be same. Whereas the potential drop across each resistor will be adding up to give the total potential drop across the circuit. Meaning, this R1, R2, R3 is there. Across each, if I take the potential difference to be V1, V2, and V3, the meaning of the second statement is potential difference across each resistor will be adding up, right? When you add the right, will be adding up to give the total potential that is supplied to the system. Okay. Now, if I take the current to be I that is supplied by the battery, then the I will be the same across each resistor. So I'm going to mathematically combine these two statements and derive a mathematical expression. So observe, what should V be equal to? V will be equal to V1 plus V2 plus V3. Am I right? That's the statement. But for me to find V1, V2, V3, I can apply Ohm's law. So you can apply Ohm's law whenever you have one potential difference source and one resistor. So if you observe across R1, the potential drop is V1. So what will be the value here? It will be I into R1 plus V2 will be IR2 and V3 will be IR2. So this can be written as I into R1 plus R2 plus R3. Okay. So R1 plus R2 plus R3. Now, what should I do with this V? So for this, I will draw another circuit where the circuit will contain replacement of all these resistors. So all the three resistors will be replaced with one resistor, which I will call it as RL. And if I take the potential difference here to be V and here the current will be I, then V will be equal to I into RS. I take the value and substitute it here. So I into RS is equal to I into R1 plus R2 plus R3. I and I will get cancelled, which implies RS will be equal to R1 plus R2 plus R3. So what happens in the case of series connection? If you need to find the equivalent resistance, you need to add individual values. If there are n resistors in series, then what will happen? RS will be equal to R1 plus R2 plus so on till Rn. So this is the whole derivation for the resistors that are connected in series. Make a note of it. Those are online, am I clear?
Yes, sir. Yes, sir.
No. Okay. So these are the concepts for today, right? So remaining concepts, as I told you, the pre-recorded version is already there. They have for the concept. After the rest, we can go through that. And I try to record the videos. If possible, I record and give you. If I update it, I'll update it. The or else you can go to the previous recording which have already been under the theory video section. So before you come to next class, make sure that you go through the concepts. I tell you what are concepts. Okay. So I hope it's clear till this point. So that's it for today. So I'll see you all in the next class. Those are online. You can find up if there are no doubts.
Thank you, sir.
Thank you, sir. Thank you, sir.
Yeah.